Well, thank you for inviting me to give this talk, and thank you for the introduction, Danny. So the talk will be on efficient volumetric and continuous MRI. Here are my declarations. Have licensing agreement with Siemens, GE, Philips, Samsung, Bruker, United Imaging, and research support from GE, as well as advisory role at Setsompop Medical and Kineticore. So in this talk, I would like to show you some of the work that my lab has been pushing forward in terms of efficient and volumetric continuous acquisitions. I want to show that with some of these technology, we've been able to get multi-contrast time series data that can be acquired very efficiently with high SNR. And we've been applying this to multi-parametric quantitative imaging, rapid multi-contrast MR exam, as well as microstructure and multi-compartment imaging. So I'll show you some of the acquisition methods related to some of these topics. And just to tie it all together with this workshop, show you that these technology will be highly applicable and potentially transformative to application at 0.55 Tesla as well as at 70. So with that, let me begin by talking about some of the work that we've done in quantitative imaging. As you all know, quantitative imaging is a good direction to go to get more precise and repeatable information, as well as to enable us to do more quantitative analysis. A popular approach over the years has been in magnetic resonant fingerprinting, which is a continuous acquisition designed to have incoherent aliasing in space, time, and contrast domain to allow us to rapidly acquire multiple quantitative parameter maps as shown. This method was invented back in 2013, so nearly 10 years ago, by Dan Ma, Mark Griswold, and their group at Case Western. Back then, it was one of the most efficient imaging method for quantitative mapping. Takes around 10 seconds per imaging slice. This is fast, but if you want to do whole brain high isotropic resolution, it can take up to 30 minutes or longer. So it's hard to clinically translate this. So over the years, there's been a lot of work that has been done to try to improve the efficiency of magnetic resonant fingerprinting. I'll highlight the major direction that we've been pursuing to make this better. So first is to utilize better volumetric encoding. So instead of doing slice by slice imaging, we move to simultaneous multi-slice and 3D acquisition, where volumetric encoding can provide us with much better SNR noise averaging, as well as the ability to do data undersampling across more dimensions to allow for higher accelerations. We've done quite a bit of work also in terms of improving the reconstruction, in particular utilizing the idea of temporal low rank subspace that was pioneered by C.P. Liang and his group at USC, where with the MRF, you can see here that the signal evolution of tissue actually live in a low rank temporal subspace. So instead of having to reconstruct 500 different images, for example, in this MRF data acquisition, you only need to reconstruct 5 or 6 coefficient basis images of this temporal basis. So this makes the problem much better posed, allowing you to accelerate much better, as well as providing better SNR as well. There's also been quite a bit of work in terms of sequence optimization, particularly through the use of camera bound, which has shown some surprising result that a less varied or less random flip angle and TR train can actually provide more unique fingerprints of tissue and provide better separability if you design it well. So putting some of these methods together, where are we now? Here's some of the latest work from the lab, where we've been able to get 1 millimeter isotropic whole brain in less than 2 minutes for T1 and T2 maps at 3T. This represents about an order of magnitude faster scan than the original method. We can utilize this technology in terms of accelerated encoding to push our resolution as well, here's 0.66 millimeter isotropic whole brain in just 4 minutes. We'll zoom in a little bit here so that hopefully, even though through Zoom, we can still appreciate the increase in resolution and detail that we can get from this 0.66 millimeter, seeing some of the perivascular space with some of this as well. So it's still quite surprising to me looking at this, that we actually have sufficient SNR to do 0.66 millimeter quantitative mapping whole brain in just 4 minutes on a clinical 3D scanner. And in really thinking about it, the reason why we've been able to do this is that we're using efficient continuous volumic acquisition, as well as an efficient reconstruction through the subspace recon that really pull all the data together and do a joint reconstruction to be able to do good encoding and as well as have high SNR. So now that I've shown you this, let's look at some of the application of or the benefit of some of these quantitative techniques. Here's an example, which is quite neat, I think, showing repeatability across scanner vendors as well as time points. Here's a healthy volunteer acquire 1 millimeter isotropic whole brain in less than 2 minutes on the Siemens scanner at the Martineau Center before I move over to Stanford. And then 6 months later, once we implemented this on the GE scanner at Stanford, we scanned the same healthy volunteer in less than 2 minutes. We align the scan, co-register the maps, and take the difference here, blow this up by tenfold, and you can see that there's very minimal difference across vendors as well as time points for this healthy volunteer, which shows great repeatability for this technique. So it's good that we're being able to scan quickly, but it's also important that we have fast reconstruction for clinical deployment. I'll highlight an example here from Gomez et al., where they've done subspace projection as well as machine learning in their reconstruction pipeline to try to achieve pretty fast reconstruction of less than 7 minutes for sub-millimeter whole brain MRF as shown. Another direction related to clinical deployment is that it's important to have realistic synthesized image to get clinical contrast. This is a big issue if you're trying to use the physics-based equation to do the synthesis, because we typically have incomplete modeling, as I would like to highlight using this example here of T2 flare, where for T2 flare, you don't only have T2 contrast, but you actually have a large amount of MT weighting. Here's a fun example that we did, where we acquire identical imaging protocol and 2 scan, one with a single slice TSE and another one with 30 slice TSE. Where in the 30 slice case, there's a lot more 180 refocusing pulse across a different slice that generates a lot more MT contrast, as you can see here in the much better contrast in gray-white matter from the example on the right. So if you were trying to synthesize this T2 flare using the T2 map and proton density from our quantitative imaging sequence, directly using physics equation, we would have got the image on the left rather than the image on the right, which would be problematic because the clinician wants the one on the right here. So this is a problem, but nonetheless, there's been promising machine learning-based solution to overcome this. I'll highlight some work by Mickey Lustig and his group on the direct contrast synthesis of MRF, where they develop a unit multi-branch approach to get from the underlying 500 time points of data directly to the synthesis shown here. Here's some of the result for synthesizing T1 and T2 flare. Here's the physics-based one. Here's the direct contrast synthesis with machine learning, comparing it to the clinical sequence. With the T1 contrast, things work pretty well, both for the physics as well as machine learning, whereas in the T2 flare, the physics-based equation fails pretty badly as expected because it doesn't have empty contrast, whereas the machine learning approach seems to do a pretty good job here as shown, getting very close to that of the clinical sequence. So inspired by some of these faster reconstruction and clinical contrast synthesis with machine learning, we've developed our own tool using machine learning to enable faster reconstruction of even higher acceleration acquisition, as well as to produce high fidelity synthetic images for MRF so that we can clinically deploy this. This is a joint work with Greg Shashek and Shiraz at Stanford and Stanford Hospital and Stanford Children's Hospital, where we're now able to get 1 millimeter isotropic whole brain MRF in just 1 minute on a clinical scanner with fast online reconstruction. Here's some of the synthesis MRF contrast that we can get from this 1 minute scan whole brain. T2, flare, T1 cube, double inversion, as well as MP range. We get all these along with the T1, T2, and proton density maps. And you can see here that this corresponds pretty well to the standard accelerated clinical scan that would have taken about 30 minutes to acquire across these 5 contrasts. So hopefully I've shown you here that with some of the technology we're developing, we're moving towards a quantitative neuroexam at high isotropic resolution in just a few minutes, with fast online reconstruction and the ability to do accurate synthesized contrast weighted images. Now, how does all this apply to low field? I've looked through the literature a little bit recently now that I have to give this talk, and I've seen that there's some promising initial result already in applying MRF to low field from the NIH and Case Western group. It's only about 2.5 times slower than at 3T, and they're able to get whole brain data at 1.2 by 1.2 by 5 millimeter in about 8.5 minutes through that stack of spiral acquisition. There's also been some nice work by the Wisconsin Medicine group at 0.35 Tesla on their MR Linux system on body imaging as well, which is nice. So based on some of this and some of the technology that we'll develop, what should we optimize and what should we target with some of this? And I think at low field, you have much reduced B0 inhomogeneity and much longer T2 star. So the pro of this is that you can do longer spiral readout as well as try to optimize some of the crime route bound for flip angle and TR to get even better SNR. Potentially with much lower B0, you can move towards the balanced SSFP-like instead of a FIS acquisition to boost SNR further. One downside with low field is that there's quite a bit of an increase in concomitant field with some of these spiral. So you have to explore some time segmented reconstruction per spiral interleave now with the subspace recon, which can be quite time consuming and a large problem to solve. But I think there are ways that we can get around it. So with some of these techniques, what do you think we should target? My target would be we should be able to acquire 1 millimeter whole brain data in around 3 or 4 minutes if we are optimizing our acquisition to boost some of the SNR with some of these things that I've mentioned, as well as utilizing some of our latest spiral projection 3D MRF, as well as the subspace and machine learning reconstruction. So if we can do that, I think that would be quite game changing for low field imaging as well. So now that I've talked quite a bit about MRF, let me talk about another promising quantitative imaging method that we've developed, which is echoplanar time resolve imaging, or EPTI. This carries on in the general theme of moving away from acquiring a few images to try to get quantitative information, and now creating movies to track the signal evolutions throughout our whole acquisition. So using an MRI as a video camera rather than a snapshot camera. So with this idea, we're going to have a lot more encoding to do. There's a large KT space to sample, and we have to come up with a nice way to sample this. So we've developed this continuous KT acquisition and spatial temporal subsampling utilizing control aliasing as well as incoherent aliasing. And then combining this with spatial temporal low rank modeling, which has been really powerful, we're able to time resolve hundreds of different images across these multi-shot EPI type acquisition that is distortion and blurring free. Here's an example of such an acquisition for a 9180 acquisition here that tracks T2 and T2 star. We're getting 112 images in this acquisition where we have an image that is distortion and blurring free at a temporal resolution here of just 0.93 milliseconds. So using some of this technique, we can combine this readout with a nice sequence that is sensitive to T1 recovery, T2 star decay, as well as T2 decay, and done in our volumic continuous acquisition. In 3D, we can get fast 3-minute whole brain scan at 1 millimeter isotropic at 3T, that we can then derive T1, T2, T2 star, proton density, as well as B1 plus from it, nicely as shown here. We've done quite a bit of work in terms of scan, rescan, repeatability of this method on healthy volunteer. Some details here where we get R1 map from our EPTI acquisition, synthesize an MP range so that we can pass it through FreeSurfer to get automatic segmentation of different brain regions. We then look at T1, T2, T2 star across these different brain regions in a scan, rescan. You can see that we have very high repeatability as well as minimal bias across these scan, rescan. With this technology, we can also titrate the resolution depending on the scan time that we have, and we can push to around 0.7 millimeter in less than 10 minutes as shown here. So at this higher resolution, let's see what we can get. We can now look at cortical depth features of these quantitative T1, T2, and T2 star at this high resolution. Again, we generate an R1 map, synthesize MP range. Instead of just segmenting the brain, we're looking at different surface reconstruction across different cortical depth, inflate these surface. Then we can look at the T1, T2, T2 star across different cortical depth as shown here, as well as across different brain regions. We can then also plot the cortical profile of these quantitative meshes across the cortical depth, as shown here for different brain region. Let's zoom into one of these brain region, and let's look at repeatability of these cortical profiles across subjects and scan, where we've seen consistent and repeatable profile across subjects as well as scan rescan, showing that we have reliable surface reconstruction from this fast scan, as well as repeatable intracortical measurements. Looking in a little bit further into this data, we can see that we nicely have a lower intra-subject variability than inter-subject variability. This points to an exciting potential that we might be able to start to detect individual differences in these cortical profile, even in healthy volunteers. Okay, so with this 9-minute scan, we can also generate, obviously, the synthesized images as seen here, and at this high resolution, you can view them at isotropic voxel view them at any viewing angle as well. So you can appreciate the high quality data that we can get across these different contrasts. Another important area that we've worked on is to be able to be motion robust as well, to get precise quantitative acquisition in clinical environment. In this case, we've added in a rapid 3D navigator during the short dead time of our EPTI acquisition as we wait for signal recovery. This 3D navigator not only tracks motion in 3D, but also tracks B0 field variation that can be created due to some of these motion. And it can track it at a fast temporal rate of around 2 to 3 seconds. Here's some of the motion tracking, as well as tracking of B0 changes. Now we did some experiments on this. Here's an example of an EPTI acquisition that is motion-free. With motion corruption due to motion as well as B0 changes, you can see that the quantitative map really start to fail, particularly with the T2 star. Now, if we track these motion and B0 and incorporate it retrospectively into our reconstruction, we can recover the nice T1 and T2 star map, comparing to the motion-free one, looking at different brain region. And you can see here that we have high repeatability across the motion-free and the motion-corrupted one that has been corrected, showing good motion robustness. So hopefully I've shown you that some of the technology we're developing here will lead to precision quantitative MR, where we're able to get rapid and repeatable quantitative imaging with even more tissue parameters acquired in a motion robust way at high isotropic resolution. So now that I've shown you that, let's see how some of this EPTI technique can be applied at 0.55 Tesla. So with this EPTI, we're doing continuous volumetric readout with minimum dead time to provide high sequence efficiency in terms of encoding as well as high SNR. This is really well suited for low field because now you have longer T2 star so that you can use a longer readout and an echo train length to really do more encoding and do better SNR averaging. We can also take advantage of the fact that we have reduced B0 inhomogeneity to be able to get better spatial temporal encoding with our KT encoding and KIPI for even higher acceleration because we're now less reliant on some of the high channel count coil array encoding. So with some of this, before we're able to get 1 ISO in 3 minutes, with some of the modification, I believe that we should be able to target 1 by 1 by 3 millimeter with sufficient SNR in a 3-minute scan to get whole brain quantitative exam from this as well. Now that I've talked quite a bit about low field, let's move on to the ultra high field part, where we've done some work on using 3D EPTI with variable flip angle to map multi-tissue compartment and modeling. Here's an example where we did 3D EPTI acquisition for multi-echo type, where we have 56 T2 star echoes as well as acquire at 9 different flip angle. So in this sequence, we'll have sensitivity to T1, T2 star, as well as frequency change across the readout to enable us to do multi-compartment modeling of myelin, axon, and extracellular water, fit with this equation on this large data, really pushing the resolution here at 70 to down to 600 micron isotropic quantitative imaging of multi-compartment model. This still takes a long time to do because it's really high resolution. Takes about 1 hour of scanning. We get a lot of data though, 8 flip angle, each one with 42 echoes. So 300-400 different images here. On a 70 tera with 3-pool model, you can see that we get really nice detailed myelin water fraction T1, T2 star, and proton density. Hopefully you can appreciate some of the nice details that we get from some of these imaging, even though I'm on Zoom here. With this high resolution, again, we can do the surface extraction using synthesized T1 weighted image that is perfectly co-register because it's from the same data. Apply the surface to the myelin water fraction maps. As well, to look at cortical depth, for example, here's the T1 map in the line of January. You see the dipped in the T1 value across the mid part of the cortical depth as expected, whereas in the myelin water fraction, you see a bump, which is correspond to what we expect. Still a bit noisy, but as to be expected, this is 600 micron quantitative maps. So with some of this, we have some limitation in SNR, so we've been pushing another technique to try to do even better. So we've been developing this Vista MRF acquisition with a double inversion preparation that allow us to do whole brain 0.66 millimeter myelin water fraction map, as well as T1, T2, and proton density in around 22 minutes at 3T now. And hopefully we can start to push this to 70 to really be able to get mesoscale multi-compartment quantitative map with good SNR in a reasonable time frame. So with that, hopefully I've shown you some of the technology we'll be developing for efficient continuous volumic acquisition in MR to allow for rapid quantitative imaging, rapid brain exam, as well as multi-compartment modeling. And I'll finish up this talk by acknowledging my groups, the institutions, and the support that I've got here. And thank you for your attention.